Good morning, everyone. So, in the previous session, we have studied the group of instructions. From that, we have seen the instruction called add, then ADDC, add with carry, then a small example on 16-bit addition, then decimal adjust, then we have seen subtract. The instruction for subtract is SUBB. This is the example for BCD addition. So whenever you have a binary addition, so this line is not required. Till here the normal addition is fine, but if you want a BCD addition, here whatever the result you got, that should be converted to into BCD format. So for that we need to write this. So we'll see how will that go. Yeah. So first the question here, they asked us to add 34 to 49. So 34 hexa value plus 49 hexa value. To add that, first I am clearing the carry bit. If I have a carry in PSW register, I will just clear that carry using this instruction called CLRC. Next I have another instruction, move a comma in immediate addressing mode I have written 34. Okay, so the first to add 34, I mean a will be equal to this, a is equal to 34. Okay, to move this a into accumulator, I have written this instruction, move a is at destination side and #34h is at source. So I have just loaded that 34 into accumulator. Next I have is, I can also move in a different register in R0 or R1 in any register 49, but instead of that what I did is I directly wrote an addition instruction here. Okay, so that means I have written add a, that means in a it already has 34 here, okay, before execution of this instruction, and 49, ash 49. So what it does is a is equal to 34, then 49, that means it takes 34 plus 49, this both will be added, so just they will be converted to binary. So 34 if you write, that will be 1 and 4 0 0. Next 4 9, when you write 4, that will be, sorry, 1 0 0. Next you need to write 9, 1 0 0 1. So addition. Okay, normal binary addition. If you do binary addition, you get 0 plus 1, you get 1, 0 plus 0 you get 0, 1 plus 0 you get 1, 0 plus 1 1, 1 plus 0 1, 1, 0 plus 1 1, here you got 0. So here this value is 7. See here, 0 1 1 1. Okay, so what you got is 7. Then here another value is 8 9 10 11 12 13. So 13 means D in hexa. Okay, you got 7DH. That means this is the answer for normal binary addition. This is the result what you get. So after executing this complete instruction, the result is 7D. Now after instruction, A will be equal to 7D. Okay, after execution of this instruction I am talking about. Okay, but here the question was for normal BCD addition. So this result should be converted to BCD format. To convert that to BCD format, to convert this hexa to any BCD format, we should always see this result, and if in LSB or in lower bits or higher bits, if you have the value greater than 9. Okay, whenever you have value greater than 9, then if it is the lower bits, you need to add 06 to it. Okay, you should add 06. If in higher bits, if you have greater than 9, you should add 60 to that. Okay, so now in this case, in this 7D, which is greater than 9, this lower bits, D is greater than 9. So to this result, you need to add 06. Okay, so for that, I'll just erase this. So the result you got was 0, 1, 1, 1, 7 and D. For that I'm adding 06 because this lower bits are higher. Okay, these lower bits are higher, whereas these higher bits are not more than 9. So here I'll add 6. To add 6, I'll write 1, 1, 0. I'll add this. These are nothing but 0 over here, all the other here remaining 4 bits. Okay. So I can write out, that doesn't matter. Yeah, so now 1 plus 1, 1 plus 0, I get 1. Okay, here I got, okay, there is no place here. 0, 1, 1, 0. 1 plus 0 I get 1, 0 plus 1 I get 1, 1 plus 1 0, 1 carry, 1 plus 1 I get 0, 1 carry, 1 plus 1 0, 1 carry, 1 plus 1 again 0, 1 carry, again 0, 1 carry and 1. Okay, and I'm also not getting any carry from this D 7th bit. So in PSW register, my carry flag will be reset. So the result what I got is 1, 0, 0, 0. That means this is 8 and 0, 0, 1, 1. That means this is 3. So after adding this 0, 6 to the lower bits of the result, I got 8, 3 as my result. So now after execution of this line DAA, what happens is accumulator will be equal to 83H. This, the end result is this 83H, the binary addition. After adding this 34 and 49, you will get 83H. Is that fine? So now see, here he has written A is equal to 7D. Before he has written this before DAA instruction execution. But after execution of that, A is equal to 83H. So 7D we got here and 83 we got here. Okay. So in this program, first you're just clearing the carry bit in PSW register, then you are loading this 34 into 8 accumulator, then you are adding that already A has 34 in it, so it is adding that 34 and 49. After adding both, after this binary addition, you get A accumulator. Result will be stored in this accumulator, the destination itself, right? So A will be equal to 7DH. But the question was BCD addition. So this 7D should be converted to BCD format. To convert that to BCD format, I need to write decimal adjust A. So this instruction means whenever you have in this 7D, whenever you have this lower bits more than 9, greater than 9, you should add 06 to that lower bits. If higher bits are greater than 9, then you should add 60. If both at a time are greater than 9, then you need to add 6 here. You need to add for higher bits, you need to add 60, and for lower bits you need to add 06. So in nothing but you are just adding 6 for higher and for lower. Okay. So then you get it in a BCD format, that is 83. Yeah, next you have here is increment is one of the instruction. Increment is the operand by 1, nothing but it increments the operand by 1. So for the example, if you write an instruction INC NCA. So in the previous case, what you took was A was equal to 34H. Now in this case, if you write increment A when A is equal to 34, what it does is it will increment by 1. So for example, how it happens inside that CPU is, see, 34. 34 means 0 0 1 1, 4 means 0 1 0 0. Okay, this is a value which is already having in A. After, when it sees this increment, it will just add by 1. Yeah, here it will just add by 1. Okay, so 0 plus 1 you will get 1, 0 1 0 1 1 0 0. So now this is a value for this is again 3 0 1 0 1, means you have 5H. Okay, so before you got 35H. Okay, so let me show you here. So before writing increment A was equal to 34. After executing this instruction, you got A is equal to 35H. Again, if you write increment A, then A will be equal to 36H, and so on. It keeps on increments by 1. Okay, so the operand can be register, direct address, and indirect address, and a data pointer. So this here, whatever operand you are writing, that can be any register like A, B, or R0 or whatever it is. Then it can also be a direct address. Direct address means you can also take increment 4 2H. So in case if you have 4 2 in case at 4 2 address location, if you have 0 3 inside this 4 2, then if you write increment 42H, then after increment this 4 2 will become 0 4. Okay, so the content whatever is present inside this 42 will be incremented. Before it was 3, then now it became 0 4. In that way, this is if you use direct address. Indirect address means if you take @R0, and for example if you are pointing this R0 to 42, okay, for some location, that means before this you are writing move R0 comma #42. Here you are writing #42H. Okay, 42H. That means R0 is pointing towards 42 and you are writing increment @R0. Then even here it happens same. So what is present where it is pointing inside this R0, that will be incremented. So the same result you will be getting. Next you have the data pointer. Increments we have seen are for register, for this register, direct address, indirect address. Now the data pointer, that means if you have increment DPTR, okay, and if DPTR is pointing towards 7002H, okay, 16-bit address. So here whenever you write increment DPTR, if DPTR is having already 7002, then after incrementing DPTR, the result you will get is 7003H. Okay, so the DPL will be incremented with 1. So in this way this occurs. Now same way, decrement the operand by 1. DEC means INC means you are incrementing by 1. Whenever you write DEC with some register or some direct address or indirect address, here it will just decrement by 1. Okay, so whenever you are doing that, if you write DEC A, if A is equal to 0 2, after execution A will be equal to 0 1. Okay, if you take instead of A some R0 or whatever register, see register, direct address and indirect address, these things if you take, then same thing, whatever content present in that will be decreased by 1. See indirect address, we'll see example for indirect address. See I am writing DEC @ R0, and if in case R0 is pointing towards 40H location, and what does 40H location have? If it is having 0 1, okay, in this I'll write this here. Yeah, if 40H is having, inside that it is having 0 1H, then see decrement @ R0 means where R0 is pointing is towards this 40H, and what is the content present in 40H is 0 1. So this will be decremented by 1. That means after execution 40H will be equal to 0 0H. It is decremented by 1. Okay, in this way this decrement instruction works. Next you have multiply AB and divide AB. So just see these instructions. In before for addition and subtraction we have written A, D, D, and we can use destination as only source. Okay, destination and source. In destination and source always destination should be accumulator only, whereas in source you can take any register or direct immediate addressing mode. Okay, in that way you can take any addressing modes in this way. But coming to this multiplication and division, always you should write in this way, mul A B. There shouldn't be any space between A and B, and then it shouldn't be separated with comma as well. Okay, you should always write A and B. Only these both registers will be used. Even for division it is in the same way. You should use A, B, div instruction space A and B. Okay, you shouldn't separate them with a comma or some space, whereas in addition and subtraction you have separated with a comma in between the source and destination. Now for multiply we'll see a small example. We'll yes, so we will take A is equal to 5. Okay, next B is equal to 7. That means I am taking the decimal terms. Okay, 5 and 7. So if I multiply, if I write MUL AB, after execution what it does is it will take in hexa and then that will convert it to binary, and that multiplication happens 5 into 7. So after that what you get is A is equal to 35. Okay, in decimal if you convert this to hexa you will get 23H. Okay, just write this in binary 35 and write it in the form of hexa. Okay, so you will get 23H. Same way if you take A is equal to 2H, B is equal to 3H. Okay, so if I write move AB, then after execution A will be equal to 06H. You need to write here 00 hexa you are writing. Yeah, so A is equal to 06H and B will be equal to, even in previous case, 00H, because you don't have any larger number. Okay, it is not exceeding 8 bits. If it is exceeding, the result is exceeding 8 bits, then B also will be equal to some value. And also generally this multiplication how you do is, if A is equal to 0 2, you will take the complete 8 bit, that is 0 0 0 0 0 0 1 0, this is 2. For 3 you have 0 0 0 0 1 1. So whenever you multiply them, you will multiply once with this 1. Okay, then after when you multiply with 1 something, you will get the same value. Okay, so again the next term you will multiply with 1 and 0, so you will again get the same value as it is if you multiply with 1 and 0. So same way you keep on do. After doing, you will add all these terms, right? So if you get a carry over here in this result, if you get a carry in the end, then in PSW register carry will be equal to 1. If you don't get, that will be equal to 0. And with that, if the result after multiplying 2 and 3, the result is not crossing any 8 bits, if the result is more than 8 bits, then the other half of it, the lower byte of the result is stored in accumulator. Okay, and the higher byte of a result will store in this b which was equal to 0, right? So this will be stored in b. So if it is storing in b, this overflow bit, you have an overflow bit in a PSW register, the d0 bit, that will be equal to 1. So whenever the result is more than 8 bits, this overflow bit will be equal to 1. Okay, so in this way multiplication works. Always remember, whenever I am multiplying two bigger numbers, okay, if I multiply two bigger numbers, for example you take 25, a is equal to 25 and b is equal to 78. If you multiply them, the answer what you get, these are in hexa, the answer what you get in hexa is, try to solve it by yourself, you will get 5811h. This is the value what you get in hexa. So that means the lower byte of the result should be stored in accumulator, right? Sorry. So the lower byte of a result should be stored in accumulator, right? So generally the result what you get is this 58h. So the lower byte should be stored in accumulator, that means 58. So a will be equal to 58 and b will be equal to 11. Okay, so here the overflow bit will be equal to 1. In this way you will get the result for multiplication. Now coming to division. Okay, so in this division you will write div ab. So this in this accumulator is divided by some number in register B. Okay, so the integer part of this quotient is in register A and the remainder is in B. So A has the quotient and B has the remainder after execution of division operation. Okay, so for this, yes, we will take a small example. We will take A is equal to 3, 5 and B is equal to 10. Okay, so when I am taking them in decimal, see when I take them here, whenever now I write an instruction. Yes, sir. Now I have written div ab. So here when I try to divide this 35 with 10, so what I get is the quotient and remainder. So the quotient what you get is in 10 table 3 times 30 will be divided, 3s are 30, then remainder you will get 0, 5. Okay, so that means here this is the quotient and this is the remainder. Okay, I'm talking only in decimal. If you want, you can convert it into hexa. So when you do this, now what is quotient? 3 is the quotient, remainder is 5. So now A will always have the quotient value, that is 3, whereas B will always have remainder value, that is 5. So after first A is equal to 3, 5, 35, B is equal to 10. Then now you are writing a dividing those both A and B. When you divide both A and B, here what you are getting is A is equal to the quotient value and B is equal to the remainder value. So in this way division instruction works. You have a logical operations here, few logical operations. So under this logical operations uh, we have these ANL or ORL. So ANL means the AND operation. Okay, so for logical you have the operations what you have are directly. He has taken an example. So generally for this you have few operations. So in logical you have A and D, okay, and you have OR operation, then you have XOR operation, then you have rotate operation, okay, then you have clear operation, CLR, okay, then CPL, complement. Okay, generally this all come under this logical operations, all these, okay, 6. Now here for AND the instruction what you use is ANL, okay. This for AND you'll use and logical AND operation ANL, okay. For OR you'll use ORL. Here you have see ANL and ORL both. Next for XOR you'll use XRL. For complement you'll use CPL. For clear you use CLR. Okay, these are the instructions what you use. And you also have here rotate operations. So for rotate you have, this is RL, that means rotate left. This is rotate left with the carry, that means from PSW register it will also take a carry. Here you have RR, rotate right. This is rotate right with carry. Okay. Yeah, so first we'll see ANL operation. So in this ANL operation and operation, what we are going to do is, for example, if I write ANL, you have here ANL A comma RN. That means the content of register Rn is ANDed with accumulator and the result is stored in accumulator itself, because that is our destination. So for AND operation what we will do is, here in case if for this instruction I am writing if A is equal to 0 0 1, okay, 0 0 0 1 0 and Rn. Okay, consider Rn is equal to A is equal to and R naught, this both. So R naught is having the value 0 0 1 0 0 0 1 0. We'll just do AND operation now. AND operation here, see, whenever you have here I have taken 0 and 0, here you will get is 0. Then here you have then 0 0, you will get 0 0 0, 1 and 1 1, 0 into something is always 0 here, okay, in AND operation. So this is the result, you get 0 0 1 0 0 0 1 0 in this way. So see, in here we can write in these different addressing modes. For example, I have taken this ANL A comma, I am taking the data to be E2H. I already have in A 15H. So how does this work? So 15 means just write it in binary 0 0 0 1, then 0 1 0 1 5. Okay, then E2 means 1 1 1 0, then 0 0 1 0. We'll calculate this now. So 1 and 0 you'll get 0, 0 and 1 you'll get 0, then 0 and 0 you'll get 0. Okay, 1 2 3. Then 0 and 0 you'll get 0, 1 and 0 you'll get 0, 0 and 1 0, 0 into 1 always you will get zeros. So you got the answer, what you got is 0 0 H. So after execution of this instruction A N L A comma R naught, okay, I have taken not R naught, I have taken this ash E2H. For this A was equal to 15H. So after execution, the result what I got was, so I'll write here before execution and after execution. This is before execution. Before execution, A was equal to 15H. Okay, and after execution, A will be equal to 00H, because whatever the result was there, that will store in the accumulator in this way. Now, same way, see here, if I take this A comma direct, so this E2 is there right here. I'll write some instruction 40H. Okay, see, direct address I'm writing, and I'm considering before execution this 40 will be equal to E2H. So after execution also 40 will be having E2H itself. This won't change, but accumulator will store the result, so you'll get the same thing. Okay, in this instruction also I'm considering A to be 15 and this 40 is having E2H, and there will be an AND operation between 15 and E2H. So after doing that, you will get 00 as the answer. So this 40 will be same, that doesn't change, but accumulator will be storing the result. So this is what happens. Same goes with R0 or R1, indirect addressing mode. Okay, so these all are the same. See, in this case you have ANL direct comma some data, right? So here what you're going to have is, see here, instead of that you will just write 40 here, 40H here, and here comma you just write ash E2H. Okay, and here instead of A you take this 40 is having 15 now, not this. Okay, 40 is having 15, you take that. Okay, so once you take that, then after adding this both, destination you have 40, right? So in 40 the result 0 0 will be there after execution. 40 will be equal to 0 0 h after execution. Okay, is that fine? So here what is he trying to say is, instead of this direct, for ports also you can take port 1 means you have 90, some direct address 80, so there we generally use that. Okay, so here see, direct and accumulator should always be in destination for arithmetic operations. Okay, it is not necessary for logical. So in this destination they have taken some direct address, so whatever direct address they have taken, you can write that. Here 0f0 they have taken, that means b register. In that way you can take any direct address here. Is that fine? Now next here you have is ANL C comma bit. Okay, that means this is a single bit operation. So this bit can be any one bit. He has taken P2.2 or P1.1 port. From port you can take any one bit, or from some accumulator also you can take one bit. Okay, ACC 0.1 or ACC 0.0. In that way you have 7 bits. 8 bits. So from that you can take any one bit and you can operate on that single bit. So if you operate on single bit, if carry is equal to 0 and if P2.2 is having 1, then the result will be equal to 0, which will stored in carry itself. Okay, is that fine? 0 and 1. 0 into something is always 1 for AND operation. So if you have 1 and 1, then the answer will be 1, which will be stored in carry bit. In this way your bit operations, single bit operations function. Now the same thing, okay, this instead of ANL we'll replace everything with ORL. See here, instead of ANL write ORL, here also ORL. Same thing, but here one only, I'll just take a small example for this. ORL A comma R not. Okay, so here I'll take for ORL A comma R naught means A will be loaded with some content and this R naught will be loaded with some content. So here I'll take the content to be I'll take A to B. I'm directly writing value here in binary. I'll take 0 1 0 1 1 0 1 0, and R naught, the content it is having is 1 0, then 1 1, then 0 0 0 0. I have taken this. Now if I OR them, the result, see, OR is whenever some 1 plus something is always, you will get it as 1. So here this is 0 or 0, you will get 0 1 plus 0, then 1 or 0, then you will get 1 0, then you will get 1 1, here also 1 1 1. Okay, so 1 plus something is always 1. So this is the answer what you got. So in the end, in destination you have accumulator, right? So in accumulator, if you see this, you will have F and 10, that means FA will be stored in accumulator. So in this way our operation happens. So you need to know first the operations, AND, OR, XOR, what are the operations, how they function. So then you can easily put them in this instructions and different addressing modes, and you can operate. So same way in all these different modes you can use the operation. So same way this last bit ORL C comma, if I take P2.2, if carry is equal to 0 and P2.2 is equal to 1, then 0 and 1 you will get 1. So 1 will store in this carry bit. In this way it occurs. Next you have ORL. Okay, this also works on bytes only. See, in this he clearly mentioned on byte size he is trying to operate this, and this ORL we are not using for this bit operation, so we are using it for byte. So we should always use them for byte operations, not single bit operations. So same way XRL, and you can write a comma r naught in this way. Okay, instructions can be written, and if you want some data, say this data is taken. So in this way you can easily operate this ORL operation. Okay, you can use XRL a comma rn, or else XRL a comma direct address, or else XRL a comma at the rate r1 or r0, or XRL a comma immediate addressing mode some data, then XRL direct comma a. So all this can be used in except the bit operation, the single bit operation. Okay, so now we'll see one small operation on this. See, here I have taken XRL a comma r0. Consider a is equal to 48h, okay, and r0 is equal to 29h, and now we'll see the result. So now result means, first we need to calculate. 48 means 0 1 0 1 0 0 1 0 0 0. Next 29 means 0 0 1 0 1 0 0 1. Now XOR operation. First, how does this XOR operation works? See, whenever you have two similar bits, okay, then you get the result as 0. If you have two different bits, then you have the result as 1. See, 0 and 1, this both bits are different, so the answer will be 1. Okay, whenever you XOR this 0 with 0, you will get the answer as 0, because both are similar. 0 and 0 XOR 0, 0, 1 XOR 1, 0, because if both are same, always the answer is 0. Okay, even this is same, so 0. See, these are different, 0 and 1, so you will get 1. These are also 1 and 0, different, 0 and 0, you will get 0. Okay, so this is the end result what you got. So after execution, a will be equal to 6 1 h. Okay, this is 6 and 1, so 6 1 h. This was before execution. A was 48 and r0 was 29 h, whereas after execution, this is after e, after execution, a is equal to 61 h and r0 will be equal to 29 h itself, because result was stored in a. It will not affect r0, it will affect only the destination side, whatever the register is present. Okay, so in these three operations, what you need to remember is, for AND operation and OR operation and XOR operation, here whenever 0 into something is always 0, okay, whatever it is, let it be 0 or 1, else 1. Okay, 0 into something is always 0. If you have both the bits as 1, then you will get 1. For OR operation, 1 plus something is always is equal to 1. Okay, else 0. Then for XOR operation, if both are same, let it be 0 0 or 1 1. Okay, if both are same, then the result will be 0. But if both are different, then the result will be 1. Okay, these are the operations you need to know. Then you can easily write these instructions in your program according to your needs. Yes, now you have complement and clear. So clear means whether you have 0 or 1 in your registers, After execution, for example, this A has 0 in this. I am taking two kinds of examples. So first kind I am taking in this, if I write CLR A in this case and also CLR A in this case, whenever I write CLR A, irrespective of whatever is there in A, automatically A will become 0 after execution. Here also, irrespective of whatever is there in A, after execution A will be equal to 0. It will just clear the register if I have a this clear. So this is using byte for bytes. Okay, but if instead of that, if I take some accumulator 7, this is bit operation, accumulator 7 he has taken here, okay, single bit operation. If I take that, only one bit inside that will be cleared. Before, when I said accumulator became 0, the complete 8 bit accumulator, that complete it became all zeros. Okay, but in this case I am talking about bits. So one single bit of accumulator, the 7th bit, this is the 7th bit, right? Only this one single bit will be equal to 0 if I write a clear. Okay, so this is about clear operation. Then you have complement. Complement means, see here also I'll take two examples. I'll write A is equal to 0 here and A is equal to 1 here. See, whenever I'm writing this, I meant to say in this accumulator I have all zeros, 8 bit operations I'm talking about. Okay, all zeros I have. So that means I'll be having 0 0 H here. Okay, so in this, if in exa if I write FFH, it becomes, so in this was in this case all will be ones, all 8 bit this A register. So whenever I write CPLA and CPLA here, what it does is, it was before 00H, before execution it was 00H. Now it after execution it will become FFH. Wherever you have 0, it will complement with 1. In this case, you before execution I had FFH, after complementing A I'll get 00H. Okay, so that means this complete, wherever you had 0 here before, in this case all will become ones. When all become ones, that will be equal to FFH. Here already when all were equal to 1, those all will become complement, that means 1 will become zeros, all zeros. So all 8 zeros, that means you will get 00H after the execution. This is for byte. Okay, now here I can use this CPL. You have yeah, also for ports, accumulator, all the bit instructions they have used. That means if I give A, it will become A bar. Okay, so for clear you are using bit operations. So here if I write, I am taking one small example for complement A. Yeah, I have, consider I have 1 0 1 0 1 1 1 1. This is the value I have. If I write this in exa, this will become AF. Okay, 10 and F. This was before execution. Now if I write CPL A, if I write CPL A, what it does is, see here I have 1, this will make complement of 1 is 0, this also 0 0 0. Here I have 0, complement of 0 is 1, 1 complement is 0 0 complement is 1, 1 complement is 0. So after execution what I get is 5 0. So before it was AF, after complementing it I got 5 0F. Is that fine? In this way this complement works. And same way, instead of complement, before here I had was AFH. Okay, if I write CLR, clear, so for this clear, see, clear means if I have let it be 1 or 0, this will clear it. It's clear, everything will be cleared, it will become reset. Okay, 0. So irrespective of whatever here you are having 1 or 0, it will make it as zeros. So after execution, this a will be equal to 00h. Before it was AFH. So this is about complement and clear instructions. Okay, so next you have rotate, swap and all these. Yes, so in this session we have studied about today this BCD addition, small example on BCD addition, how to do this. First do normal binary addition by using these instructions, then just to convert into that BCD format we have taken DAA. In exam if they ask you the question for BCD addition and if you write only till here, then your solution is wrong because you won't get a BCD format result. Okay, this is normal addition, binary addition. So for BCD addition you should always write this DAA. Next we have seen this increment in instruction, decrement, multiply AB, divide AB. Then logical operations we have seen, AND operation, OR operation, XOR operation, complement and clear. Okay, in the next session we'll see the other operations. So thank you.